Hello friends, this video on structure of atom part 17 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 16. So the question says, when an electromagnetic radiation of wavelength 300 nanometer falls on a surface of sodium, this is my sodium surface, let's suppose. I have my electromagnetic waves of 300 nanometer falling in this. Electrons comes out with a kinetic energy of 1.68 into 10 to the power 5 joule per mole. Please note, this is joule per mole. It's talking about per mole. What is the energy required to remove electron from sodium? So what does this mean is, this wavelength of energy was given. This wavelength of energy was used to remove electron plus give kinetic energy. So I can say that energy from radiation was divided into energy to remove electron plus kinetic energy that electron has got, right? So you have some energy of radiation that was used to kick out one electron, that is to energy to remove electron, plus the kinetic energy which electron has got. Correct? So we have to find minimum energy to remove electron. That means we have to find this part. Energy of radiation we can easily find because we are given the wavelength of the radiation. Correct? So let's find E of radiation is nothing but, since we have wavelength, so we'll use SC by lambda of this formula. This is nothing but 6.626 into 10 to the power minus 34 joule second into C is speed of light 3 into 10 to the power 8 meter per second divided by wavelength, that is 300 nanometer. I'll convert this into meter, 300 to the power into 10 to the power 9 meter. So if you solve this, you get answer as 6.626 into 10 to the power minus 90 joule. This is for one molecule. This is energy of radiation, one molecule. But the kinetic energy is given per mole. So let's convert this into per mole. So let's write energy of radiation for 1 mole. For 1 mole it will have this 6.023 into 10 to the power 23. This is per mole into, will multiply with this energy we have got, right? 6.626 into 10 to the power minus 19, right? Because 1 mole has this many molecules. So what you will get is 3.99 into 10 to the power 5 joule per mole. So joule and the energy in joule per mole for this radiation is 3.99. Correct? So if you put this value in this equation 1, what you get is 3.99 into 10 to the power 5 joule per mole is equal to energy to remove electron plus kinetic energy, that is 1.68 into 10 to the power 5 joule per mole. So if you solve this equation, what you will get, energy to remove electron will be nothing but 3.99 minus 1.68, that is 2.31 into 10 to the power 5 joule per mole. So that answer I have got. The minimum energy required to remove electron from sodium is 2.31 into 10 to the power 5 joule per mole. Now the question is, what is the maximum wavelength that can cause the photon to emit? So in that case, we'll use this much energy itself, because see, any extra energy we use, that converts into kinetic energy. So we'll assume that there is no kinetic energy to the electron. We just want a wavelength that will eject the electron out. So we'll use this one, right? So this is joule per mole. I can find per molecule also very easily. So this joule per mole, I can write energy to remove per molecule, not mole, molecule will be 2.31 into 10 to the power 5 joule per mole divided by 6.023 into 10 to the power 23 moles. So what I'll get is 3.84 into 10 to the power minus 90 joules. So per molecule, this is the energy required, and this will come from, we'll use the same formula Sc by lambda, because we want to find the wavelength which can give this energy, right? So we'll use the same formula now. We'll put H is equal to the Planck's constant, C is 3 into 10 to the power 8. So we'll solve for this, and we'll solve, we get lambda as 517 into 10 to the power minus 9 meter, and that is nothing but 517 nanometer, and that is my answer. Correct? Easy one. See, what I have done is, in this case, I found the wavelength of radiation was given. I found the energy per molecule, then I found the energy per mole because everything was in mole. And then with that, I was given the kinetic energy of the electrons. I found the minimum energy required to remove an electron from the sodium metal per mole. Since it was per mole, I converted into per molecule because I wanted to find the wavelength. I got this per molecule, this many joules, and then I use this is nothing but Sc by lambda, right? The energy is nothing but Sc by lambda per molecule. Then I have used this formula and I got the lambda as 517 nanometer. Let's take one more example. The threshold frequency of a metal is 7.0 into 10 to the power 4 per second. Calculate the kinetic energy of the electron emitted when the radiation of frequency of this hits the metal. It's a pretty easy question again. See, there is a metal whose V0 is given, that is 7.0 into 10 to the power 14 per second, and we define the kinetic energy of the electron. This is right, the electron comes out. We define the kinetic energy of this electron where the frequency of this radiation is nothing but 10 to the power 15 per second, or nothing but 10 into 10 to the power 14, because the power is 14 here, I'll make it 14. So this becomes 10 into 10 to the power, this becomes 10 into 10 to the power 14 per second. So we know that kinetic energy is nothing but half into mass unit square, and this is nothing but H mu minus mu naught, where mu is the frequency of the radiation, this guy, and mu naught is the frequency of the metal. Let's put the value. H is what? 6.623 into 10 to the power 20 minus 34 joule second. What is the value of mu? Mu is 10 into 10 to the power 14 per second, and mu naught 7 into 10 to the power 14 per second. So to solve this, you get something like this: 1.988 into 10 to the power 90 joule. This is the kinetic energy of the electron. Easy question. Let's take one more question. The Vivid Bharati station of Delhi broadcasts a frequency of this kilohertz. We have to find the wavelength of electromagnetic radiation emitted, and we have to find which part of the electromagnetic spectrum it belongs. The frequency is given 1368 kilohertz, that is this many hertz. We have to find the wavelength. Lambda is c by v, we know that. C is speed of light, 10 to the power 8 into meter per second, by v is 1368 into 10 to the power 3 hertz. You solve this, you get 219.3 meters, and that is my answer. So it comes in the radio waves. Let's take one example. The wavelength of the visible spectrum extends from 400 nanometer to 750 nanometer. Express this wavelength and frequency. Easy only. So let this be lambda 1 and this be lambda 2. So let's find V1. V1 is equal to C by lambda 1. C is 3 into 10 to the power 8 meter per second. Lambda 1 has to be in meter. 400 nanometer is nothing but 400 into 10 to the power minus 9 meter. You solve this, you get 7.5 into 10 to the power 14 hertz. Similarly, frequency 2 is nothing but C by lambda 2. C is 3 into 10 to the power 8 meter per second. Lambda 2 is 750 nanometer. Is nothing but 750 into 10 to the power 9 meter. You solve this, you get 4 into 10 to the power 14 hertz. So the frequency ranges from this to this, and that is my answer. Easy one. We have to find the wave number and frequency of a yellow radiation having wavelength of this. Wave number is nothing but 1 by lambda. So let's put the value 1 by 580 angstrom. So 1 angstrom is 10 to the power minus 10 meter. 1 angstrom is 10 to the power minus 10 meter. This is what I get. So you solve this, you get 1.724 into 10 to the power 6. And that's my answer. Find the energy of each of the photons which corresponds to the light of frequency, this hertz and wavelength of. So if you note, question talks about two different photons. In one photon has the frequency of this, the other photons has the wavelength of this. So formula we know, if you have the frequency, the formula is E is equal to h mu. You want to find the energy of photon. This become h is Planck's constant 6.623 into 10 to the power minus 34 joule second into frequencies 3 into 10 to the power 15 hertz. 15 hertz is per second. So if you solve this, this becomes 1.988 into 10 to the power minus 18 joule. So this is first case. Second case, photons has a wavelength of some value. So we'll use the formula hc by lambda. Same thing, h is Planck constant 6.623 into minus 34 joule second. C is speed of light 3 into 10 to the power 8 meter per second. And lambda is here 0.5 angstrom, that is 0.5 into 10 to the power minus 10 meter. Please note everything as you see I am converting into SI unit. And this gives 3.98 into 10 to the power minus 15 joule. And that is my answer. Correct. So here you have to find wavelength, frequency and wave number of the light whose period is this much. So we know that frequency is nothing but 1 by period. So let's find the frequency first. 1 by 2 into 10 to the power minus 10 seconds. That is nothing but 5 into 10 to the power 8 per second or hertz. This is my frequency. Frequency is done. Correct. Wavelength is c by mu. Frequency. C is speed of light 10 to the power 8 meter per second. And frequency is we have found 5 into 10 to the power 8 hertz. So you get here 6 into, sorry, you got to the power 9 here. So here you get 9. Here you get 6 into 10 to the power minus 2 meter. This is my wavelength. We talk about wave number, that is nothing but 1 by wavelength. That is 1 by 6 into 10 to the power minus 2. That is 100 by 6. That is 50. That is my per meter and that is my wavelength. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.